Hello, I'm Mike Douglas, and this is the New Technologies in Mathematics seminar of the CMSA at Harvard University. And today we're delighted to have Timo Schick, who's a research scientist at Meta AI, and he'll tell us how language models can teach themselves to use tools. So as I always do, I offer to watch the chat. So if you have a question, you can ask your question, or you can type it into the chat and I'll relay it to Timo, or perhaps answer it myself. And of course, there'll be a few minutes for questions at the end. So with that, Timo, please.
All right, thanks. And hi, everyone. So also welcome from my side to this presentation about a recent project that we call Toolformer, where our aim was, as this title suggests, to show that language models can teach themselves to use tools. And I'm going to start this talk in a very similar way to many other talks that I've seen recently, which is by showing some examples of me interacting with ChatGPT. So here's the first example I want to show you. I asked that model a simple question: who is the current president of Germany? To which it replied, as of my knowledge cut off in 2021, the current president of Germany is Frank-Walter Steinmeier, which is not a terrible response. There's a lot of language models that would hallucinate something, make something up. So this is a very solid response for a large language model, but still it's clearly not what I asked for. The language model did not provide me with the current president of Germany. To give you one more similar example, I also asked, what day of the week is it today? The answer you get from ChatGPT in that case is, I am sorry, but as a language model AI, I do not have the capability to access current time or date information. So again, a valid answer, but still not really helpful to a user. And then finally, if you ask ChatGPT the result of this equation, it will very confidently give you an answer that is just wrong. Now, what those three examples have in common is that, in my view, they can be addressed with a single solution, and that is to give the language model the ability to access external tools, the ability to ask tools for help whenever it can't write a meaningful completion by itself. So if you look at those three examples here, in the first case, clearly a search engine or some up-to-date retrieval system would have been helpful. In the second case, accessing a calendar would help. And in the final case, obviously using a calculator would be very helpful. Now, we were not the first ones to have this idea of giving language models access to external tools. But I would say that all the previous approaches can roughly be divided into two categories. The first category tries to teach models to use tools using human annotations. That requires large amounts of human annotated data. So you have to find good examples where tool use might be helpful. You have to ask humans to use those tools, record that, and then use imitation learning for your model to do the same. One issue with that is that it's very expensive. You actually need someone to annotate all that data for you. The other issue is that what a human might find helpful could be very, very different from what a model would find helpful. To give an example, if I was asked about, let's say, the birth date of George Washington, I would have no idea. I would definitely have to use a search engine to get that information. Whereas many language models, especially if they're trained on, let's say, Wikipedia-like data, have probably seen that birth date many times and can remember without looking it up. So they don't really need to use a search engine in those cases. On the other hand, if I was asked to add two numbers, like let's say two-digit numbers, I'd probably do that in my head rather than asking a calculator. Whereas especially smaller language models would definitely need a calculator to get those to get this addition right. So whether a tool use is helpful or not is really different between humans and models, and also between two different models. It can be very, very different. All right, so that is the one approach that was used in the past. The other one is that people would design specific few-shot prompts that show a language model how to use a tool to solve a specific task. Now, obviously, that only gives the language model the ability to use a tool in a very task-specific setting, It also typically only works for a single tool. And one issue with that approach is that if you show the language model examples of using that tool, it would always want to use that tool in future examples, regardless of whether it's useful or not. Now, what we wanted instead is we wanted a language model to be able to decide for itself when and how to call which tool while it writes text. And all of this should not hurt in any way its key ability to just do language modeling to predict good continuations for a piece of text. So how do we do this? Well, our idea in Toolformer was that we start from a standard language modeling data set, the kinds of data sets that we always use to train those large language models. So this could be something like CCNet or C4 or web text, any of those data sets that just consists of regular text, like this sentence here: Pittsburgh is also known as the Steel City. And our aim in Toolformer was to transform this data set into a data set that is augmented with API calls that are just interleaved with the text. So for example, in this data set, we might find an instance like this one here: Pittsburgh is also known as, and then we have an API call to a question answering API, with the parameter being what other name is Pittsburgh known by. Then we get a response from this API, Steel City, and after that we continue with our text, we continue with the Steel City. So this is the idea, starting from a language modeling data set. We want to get that data set with API calls and then just fine-tune our model on that. But obviously the question is, how do we get to this augmented data set? The way we do that is we proceed in 3 different steps shown here. First of all, we sample API calls using our language models in context learning abilities. We'll get to that in a second. Once we have our API call sampled, we execute all of them. Then crucially, we filter them to only keep the ones that are really helpful. And that is how we get our data set with API calls. So let's go through each of those 3 steps in more detail, starting with the sampling of API calls. At this point, we just start from our language modeling data set that is text only, and we just want to obtain a huge amount of potential API calls that might be useful. So at this stage, we are perfectly fine with generating a lot of API calls that are not useful, as long as we can also generate some that might prove useful later on. How we sample these API calls is fairly simple. For each API, we just write a in-context prompt that shows the language model a few examples, and we hope that from that it can generalize to new examples. So to give an example for this question answering API that I just showed, we would use a prompt that looks a bit like this one here. We would tell the model, your task is to add calls to a question answering API to a piece of text. The questions should help you get information required to complete the text. You can call the API by writing QA question, where question is the question you want to ask. Here are some examples of API calls. And then typically we would have 3 to 5 examples. In this case, I've shown just one, where the input sentence is Joe Biden was born in Scranton, Pennsylvania. And then the output is that same sentence, but with 2 API calls inserted. So that is the context that we give to the language model. And then the interesting bit is we would now give a new input shown as X here. That could be any of the texts in our language modeling corpus, and we ask it to produce an output for that. So let's see how well that works with our example sentence from before. Pittsburgh is also known as the Steel City. And what we're using here and throughout this talk is a language model called GPT-J, which is a 6.7 billion parameter language model, so relatively small for today's standards. But we're going to see that even with that model, things seem to work quite well. All right, so if we give all of this as an input to our GPT-J language model, and then we just sample multiple outputs from it. The first one that we get is this one here. Pittsburgh is also known as, and at that point, it decided to insert an API call with a question: in which state is Pittsburgh? So not super useful because we don't really need that information to complete the sentence. But then if we sample once again from that language model, it might produce something like this here, with an API call at the same position, but now it's asking what other name is Pittsburgh known by, which of course is a much more useful question. And then if we sample one more time, what we got in this case is the API call with the question, what is the second city in Pennsylvania? Now, this question doesn't make a lot of sense because there aren't just two cities there, but that is one of the things we need to be aware of. If we work with a language model that is not super big, we might end up getting a lot of those noisy API calls that don't really make much sense. So whatever method we design, we need to keep that in our head, that we need to have something to work with those low quality API calls and ideally filter them out. There are some tricks involved in order to make this more efficient, because our language modeling corpus will be quite big. There will be millions of documents in there, and annotating all of them with API calls can be really expensive if you do it naively. So there's a few tricks that we implemented to make this faster, but I'm not going to go into detail right now. You can, of course, always look that up in the paper. All right, so we have our API calls. We have sampled them for different APIs. And as I've just shown, we can do that with millions of APIs. But we will, sorry, not with millions of APIs, but we can do that with a few APIs to get millions of API calls, but most of them will not really be useful. Our next step is quite an obvious and easy one. Once we have all those API calls generated, we want to execute them. So we want our APIs to actually give us some results for all the questions that we've asked, or all the calculations that we want to do, etc. How this is done, of course, depends on the API, depends on the tool that we want to use. This might be something complicated where we need to call another language model. It could also be something very simple, like just adding two numbers using a calculator. In the case of the question answering tool that I've shown so far, things are fairly simple. We just use another language model that was trained to answer questions using retrieval. We feed it all those questions, and then we get answers. For example, in the first case, we got Steel City from our system. In the second case, we got Pennsylvania. And in the third case, we got Pittsburgh, which doesn't make a lot of sense. But of course, the question itself already doesn't make a lot of sense. So that is the second step, super simple. We just use our APIs to get our results. And then we get to the third and perhaps most important bit. Now we have those millions of API calls, 90 or even 99% of them will probably be useless. We need some way of filtering them and making sure that we only keep the ones that are actually helpful to our language model. So we need some notion of helpfulness, some way to define whether an API call was helpful or not. And I'm going to show you how we do that using a single example, which is the same example that we've seen before. Pittsburgh is also known as the Steel City. And we're going to look at a single API call and see how we can determine its helpfulness. For that, we are going to need two very simple equations. The first equation is shown here on the top. This equation defines a loss parameterized by this star here. And the loss is just the negative log likelihood that the language model assigns to the continuation, the Steel City, which is exactly what came after all the API calls that we've looked at so far. So we look at the probability of this continuation, the Steel City, given some prefix. And we're going to look at three different instantiations of this simple loss here. The first instantiation is what we call the no API variant. So in this case, we just look at our language model. We don't use any API calls at all. We just give it the original prefix, Pittsburgh is also known as, and then we look at how likely our language model finds the continuation, the Steel City, given that prefix. We look at the log likelihood or the negative log likelihood of that continuation. Let's say in our example that we end up with a loss in that case of 2.5. Obviously, the exact number we get here really depends on our language model and whether the language model already knows that Pittsburgh is the Steel City or not. So that's the first instantiation. The second one is what we call the input-only variant. In this case, we give the language model access to our generated API call, We've just used what other name is Pittsburgh known by one in this case, but we do not provide it with the answer that we got from the API. You can see here that instead of the answer, we just have this question mark symbol. And then again, we give it the original prefix, Pittsburgh is also known as, and we compute our loss. For example, here we might get something like 2.1. There isn't any additional information in what we've provided here, so the loss might also be the same. But just given how our language models work and how noisy they often are, we have to expect that the loss might be a bit different than what we've seen before. It might be a bit higher or a bit lower. And then finally, and most importantly, we also look at a third instantiation of our loss. This is what we call the full API loss. So in this case, we really give the model the API call, including the response, Steel City. Then we again give it the prefix, Pittsburgh is also known as. And now once again, we compute the probability of the Steel City. And in this case, our API call actually provides some very useful information because now it gives us exactly the answer that we need to do that continuation. So in this final case, we can expect the loss to be much lower than in the previous two cases. So this allows us to now define the helpfulness of an API call. And we do that by first looking at the minimum loss that we get from the first two cases, the no API and the input only case. And then we look at the minimum of those two losses and compare it to the loss that we get from the full API. And obviously, we want the loss to get lower as we use this full API setting. So we define our helpfulness as the minimum of the first two losses minus the loss that we get from the full API case. In that case, we would end up with a helpfulness score of 1.3. I think we have a hand raised. If you want to ask a question, just go ahead.
Hey, Timo, just a quick question regarding this example. Let's say, like Pittsburgh has also other nicknames as well. So how would you be able to take that into account when you're trying to figure out if the model is performing properly or not?
That is a very good question. In fact, if the question answering system would return some other nickname, that would certainly not be a helpful API call in this case, even though it would be a correct answer. The thing about our approach here is that we actually throw away all the examples where an API call is not helpful. We don't actually teach the model that an API call was not helpful. We basically only keep the positive instances. This means if the model if the question answering system gives us a different nickname, we might not end up finding a helpful API call in this case here. But hopefully we would still find helpful API calls in enough other cases that the model would still learn something. But you're absolutely correct. This is kind of an ambiguous case. Ideally, we would want a kind of more powerful question answering tool that could give us multiple answers. We haven't experimented with anything like that in this very simple version of our question answering tool.
Okay, thank you.
Sure, you're welcome. All right, so we have our helpfulness defined. There are two things that I want to point out here. One of them is that obviously this helpfulness score that we get really strongly depends on the model that we're using. And this goes back to something that I've said earlier, where we said what is helpful really depends on the model that we're using. So if you think about using a different model, maybe we're using like a GPT-3 with 175 billion parameters, and that model already knows that Pittsburgh is known as the Steel City. In that case, our loss in the very first case, in the no API case, would already be much lower because the model already knows how to continue that sentence. And so accordingly, our helpfulness score might be much lower, might even be negative. And so it really depends on the specific model that we're using, whether an API call is considered helpful or not. The other thing I wanted to point out is, as you can see here, I've always put the API calls at the very beginning, despite our model actually making them at a very specific position. The reason for that is that right now we're working with a model that has not been fine-tuned on any API calls. So if you give it some text and then suddenly there's an API call, which is something that it hasn't seen during pre-training at all, that would kind of completely interrupt the flow. That would give us a pattern that the model hasn't seen yet. And so accordingly, the probability of the continuation would always be much lower because the language model wouldn't even know that it needs to continue the sentence that came before the API call. This is why at this point we use that kind of trick where we always put the API call at the very beginning. We still incorporate the position where the model has made the API call, because this determines which part of our text we give to the model as a prefix and over which part of the text we compute our loss. All right, let's look at one more example. Let's take another API call from the ones that we've just seen. So in this case, let's take the one where the model asked in which state is Pittsburgh. Again, in our input-only variant, we might get a loss that is roughly the same as the original one because we don't really add any useful information. Let's say we get 2.4 in this case. But then in the full API case, again, we don't provide any information that is useful for predicting the steel city. And maybe the fact that we're introducing the word Pennsylvania here even confuses the language model. So we might end up, let's say, with a slightly higher loss of 2.6. And if you compute the same helpfulness score once again, in this case, we end up with a slightly negative helpfulness score of minus 0.2. All right, so we have our way of defining whether an API call is helpful or not. But so far, we've only looked at this single question answering API. So I just want to spend 1 or 2 minutes to show you a few more examples from all the APIs that we've experimented with in the paper with corresponding actual helpfulness scores that we get from a GPT-J model. So here, first of all, is another example of our question answering tool. The text that you can see here, or all the text that I'm going to show, are just small snippets from the actual language modeling corpus that our model was trained on. So we just took those random millions of texts and annotated all of them with API calls. And so here's one example where the text goes, the Nile has an approximate length of, and then the model decided to do an API call to our question answering API asking, what is the approximate length of the Nile? It got the response and then continued the sentence. And given that the exact number of kilometers is used here, that API call was very helpful to the model with a helpfulness score of 2.08. Another tool that I've also mentioned in the very beginning is a calculator. So here's one of the examples in our data set where the model decided to use a calculator. If Venice had an atmosphere similar to Earth's, then you would expect Venice's main temperature to be 499 Kelvin rather than 735 Kelvin, which is 1.47 times hotter. And to get to this number 1.47, the model decided to use a calculator and just divide 735 by 499. So again, given that the model isn't good at doing that computation itself, that API call is very helpful with a helpfulness score of 1.59. Another tool that we use is a calendar. That's a very simple tool that would just give you the current date. There are certainly more complex instantiations of a calendar that you might think of, but for the sake of simplicity, here we just said our calendar tool can give you the current date. And one example where that was useful is this sentence here. The WL will be open on Friday, March 10 and Sunday, March 19 for regular hours. And then after the term Friday, the model decided to ask about the current day. And that was for this particular document in our language modeling corpus, Thursday, March 9, 2017. And of course, knowing that today is Thursday, March 9, makes it very likely that the Friday that is being talked about is the next day, March 10. So again, that was a helpful API call with a score of 2.11. There's 2 more tools to go. One of them is a search that allows you to search through Wikipedia using a simple BM25 retrieval system. We don't have to read all that text, but basically the model can enter a search string and it will get the best matching snippet from Wikipedia. And then the final tool, also very simple, is a translation system. We just experimented with translating from any language into English, no other directions. So here we have a document that starts with, I'm not going to read that because I actually can't read the language, but basically it starts with the best schools in Jersey. Translating that into English helps making the prediction that this page is actually about universities and colleges in Jersey. And so the helpfulness score is 0.7 here. Now, I've shown you quite a few examples of helpful API calls. I also want to show you a few things that we get at the other end of the spectrum, some API calls that are borderline helpful or really not helpful at all. So here's one of those cases using the calendar where the text is enjoy these pictures from the Easter egg hunt. And we can see that the date of that text was Friday, April 13, 2013, which is around Easter. So this is like a bit helpful because it makes it more likely that we're talking about an Easter egg hunt compared to, let's say, some Christmas event or something else. So we still get a slightly positive helpfulness score of 0.33. Then there's also this example here where the model uses the calculator, but in a way that doesn't make any sense. It just divides two numbers without any clear reason for why it want to do so. Accordingly, the helpfulness score is negative. And then here's an example where the text is the last time I was with him, I asked what he likes about me. And the model decides to ask the question, who was the last time I was with? To which the response from our question answering system is the last time. So this really doesn't make any sense. And accordingly, we get a very low helpfulness score. All right, we have those helpfulness scores. Now, the only thing that remains is we need to set some kind of threshold to decide how helpful an API call needs to be for us to include it in the training data. So what we did is we annotated a subset of our language modeling corpus consisting of 2.5 million documents with API calls. And then for different thresholds, we looked at how many API calls would remain. And so you can see here for a threshold of 0.5. So if you keep all the API calls that have a helpfulness score of at least 0.5, you can see with how many API calls we end up for all the different tools that we've looked at. And you can see that all of those numbers are pretty low, which of course shows you that what we're doing here is not really efficient because we are annotating 2.5 million examples with way more than one API call per example. So we might have, let's say, 10 million API calls, and then we only end up with between 200,000 and 3,000 of them actually being helpful for this threshold of 0.5. There are various reasons for that. One of them being that our model is relatively small, so it's not really good at doing those API calls in a few-shot way. And we can discuss at the very end some ways of making this more efficient. Another thing I'd like to point out is we can see that for the calculator and machine translation system, the number of helpful API calls is particularly low. There are two reasons for that. One of them, if you look at a random web document, there just aren't that many examples where using a calculator would actually be of much help compared to, let's say, searching something on Wikipedia or knowing the current date, which just is useful for way more documents. When it comes to machine translation, one thing to be aware of is that this corpus that we use, the data set, is actually one that is supposed to only have English texts. So there was some pre-processing to remove all non-English text. Now, this pre-processing wasn't perfect, which is why we still end up with a small amount of documents containing non-English text. But the vast majority of those 2.5 million documents is English only. And that explains why machine translation is only helpful for so few examples. We also looked at what happens if you increase that helpfulness score to, or the threshold to 1. In that case, we get the numbers shown here. And so based on those plots, what we ultimately decided to do is to use a helpfulness threshold of 1 for the Wikipedia search, calendar, and question answering system, and a threshold of 0.5 for the other two tools, just to make sure that we have a certain amount of examples for those. This is one of the things that we did not empirically validate for a few reasons. One of them is it's very expensive to do those ablations, but also because we were interested in zero-shot performance of our models. We did not want to do a lot of fine-tuning by looking at, or like a lot of hyperparameter tuning by looking at how different choices would affect our downstream results. So this is definitely an interesting question for future work, whether there's more elegant ways for picking those thresholds instead of looking at those plots. All right, we're almost done with our process to get to our final data set. We have now filtered the API calls. The only thing that remains is that we actually merge all of them. So we do this entire pipeline for each API independently, but of course over the same text, so that in the end we can merge all of that together and we end up with a data set where we have examples for all the different APIs that we care about. All right, we've made it from our original data set to one that has API calls, and those API calls are specifically selected in a way that they are helpful for the model that we've been working with the entire time. So the next and final step is to fine-tune our model on that data set. Crucially, it should be the same model because that is the model for which those API calls are helpful. But apart from that, the fine-tuning is very straightforward. So I wouldn't go into detail about that. It's just regular language model fine-tuning. Something important I'd like to point out here, and we'll also get back to that later, is that because we've basically used the same data set that our language model was trained on in the first place, by doing this additional fine-tuning, it should not lose any of its generality, it should not lose any of its skills, because it's fundamentally still trained on the same distribution, just with some extra information on top. All right, but let's, of course, also look at how things really work if we do all of that. Let's look at some results that we get with models trained with this approach. We're going to look at a few tasks. The first one is the Llama benchmark, which, in case you're not familiar with it, is a simple benchmark that just consists of sentences that a model needs to complete. And in order to complete those sentences, you need to have some factual knowledge. So, for example, a sentence might be, Joe Biden was born in the year, and then you need, or the model needs to fill in the year. And that is basically how that data set is built. It consists of 3 different subsets. One of them is the squad subset, which we can see here. And in particular, what we can see is the accuracy on that data set that a GPT-J model, a 6.7 billion parameter language model, gets without any tool use, without any tricks. Just taking the model out of the box for that data set gives us an accuracy score of 18. Now, another important baseline to look at is what happens if we continue training our GPT-J model on the language modeling data set that we use, which is CCNet, because we know that most of our models are undertrained. So just training them for longer on the same data usually gives us some improvements. And so to make our comparison fair, we also have this baseline where we train our model on the same portion of the data that we use to generate API calls, but this training is without any API calls. And we can see, as expected, that our model gets a bit better, but not by much. And so finally, we also want to look at our model trained on API calls on that same CCNet data, but with API calls that we've just generated in that 3-step pipeline. And we call that model the Toolformer. The first variant of the Toolformer is one where we train on all that data, but then at decoding time or at inference time, when we evaluate the model, we actually prevent it from doing any API calls. This is what we call the Toolformer disabled. And we can see here that, interestingly, that model, despite not being able to use APIs at evaluation time, still performs a bit better than the other two. So apparently, even learning to do API calls, learning to predict when and how to do API calls, learning to predict how the responses might look like, seems to contain some useful signal, making the model better on this task. But then let's finally get to our Toolformer in an enabled variant where it actually can use APIs. And we can see here that our score goes up to 34%. So we see a massive improvement from this ability to use APIs. In this particular case, and for all of Llama, the improvements we see come from the model using the question answering API. So it was just ask that API for the missing facts, for the missing pieces, and then use them to complete the text. We can also look at 2 more baselines, which are much bigger language models than our 6 billion parameter GPT-J. Here we have results for OPT, which is about 10 times larger, and then also for GPT-3 with its 175 billion parameters. So we can see that, at least in this particular case, our Toolformer outperforms those 2 much bigger models, despite being smaller, simply because it can use those tools that are very, very helpful for it. Things look very similar for the other 2 subsets of Llama. So here we have the Google RE subset with the exact same trend. And here we have the T-Rex subset, again, showing the same trend that we've also seen for the other subsets. All right. One thing I should mention here, of course, is that all the results I'm showing here zero shot. And this is true for all the examples that we're looking at. So there is no further fine-tuning involved. There are no examples involved that the model sees. And that also means in terms of using the API, it needs to decide for itself whether to use an API, and if so, which API to use. We do not give the model any hints whatsoever. And so this is quite nice to see that the model actually decides, in I think more than 90% of the cases, to use the question answering API, despite us not really telling it. So all of that just comes from the pre-training. The next benchmarks I want to look at are a few benchmarks that test the mathematical abilities of language models, in particular ASDiff, SWAMP, and MOPS, shown here in those plots. And again, for those benchmarks, we did not tell the model in any way that it should use a calculator. We just gave it the original task input. We asked it to produce an output in a zero-shot way. And we can see once again that using the calculator in this case is super helpful, and also that the model decides to use the calculator in, I think, around 90% of the cases. And again, we see huge performance improvements even over those much bigger language models. Things look very similar for our third set of tasks, which is question answering, as long as we only look at our 6.7 billion parameter baselines. So for those, we can still see that our Toolformer clearly outperforms all the other baselines. But what we can also see here is that actually GPT-3 performs better than Toolformer, despite the latter using a question, using APIs. One thing I have to say here is, because for question answering, it would be so trivial to just use the question answering API, we actually disabled that API for this experiment, because we wanted to see whether the model could use the Wikipedia search to find the right information for itself. If we were to use the question answering API, numbers would look much better here, but that would feel a bit like cheating, because that task would be very, very tailored towards that specific API. And so the reason why we're only seeing a modest improvement and why the model does not match the performance of GPT-3, GPT-3 is already very good at those tasks, simply because it is so big. It has a lot of capacity to remember exactly those facts that are being asked in those data sets. And also doing the Wikipedia search, we implemented that in a very naive way. We just use a BM25 retrieval. So in many cases, the model would do a search that actually makes a lot of sense, but the result that our search engine returns just isn't very useful. All right, one more of these slides, one more set of results I want to show before we can move on to something else, is this here. We have two missing tools that we didn't look at yet. One of them is our calendar. The other one is our machine translation system. In terms of the calendar, we first evaluated on Llama, which is like a variant of the Llama data set that I've shown you earlier, but with different timestamps. So for example, it would say the current president of the United States is, and then the model would have to give different answers depending on what year it is. And we can see here that Toolformer gives us some improvement, but this is actually a negative result, because the improvement only comes from the model using the question answering system. So despite the time being so crucial, in those cases here, the model almost never decided to actually use the calendar API. Instead, it would either use the question answering or the Wikipedia search tool. It has not really learned that it should use the calendar in this case. We also have this other data set called dateset, which contains of a lot of questions that in a very explicit way require you to know the current date. For example, that would be questions like, what day is it tomorrow? How many days until Christmas? When was the last Saturday? Those kinds of things. And for that, we can see that the model has learned to use the calendar and is also profiting a lot from it. And then in terms of machine translation, we also have quite mixed results. The data set here is one where you would have to answer questions. The questions are given in one language, but you need to provide the answer in another language. So it's kind of a synthetic setup. We can see here that, first of all, as we move from GPT-J to GPT-J fine-tuned on CCNet, performance actually drops from 11 to 10. So it seems like our portion of the corpus that we fine-tune the model on is a bit less well-suited for multilingual stuff, which makes sense because we filtered it to not contain any non-English text. And then using our machine translation API gets that score up again to 11. But still, this is not very impressive. We would have expected to see larger gains here. And we are still exploring a bit why this is not working better than, or why this is not working as well as we would have expected. All right, one more set of results that I want to show you, because I said earlier that the advantage of our method is that our language model does not lose any of its generality. It is still like a language model that you can use for all kinds of things. And to prove that that is actually the case, we looked at whether its language modeling abilities get worse as we do that kind of API fine-tuning. So we looked at perplexity of our language model on 2 different language modeling benchmarks. First of all, we looked at Wikitext, which is just a subset of Wikipedia. And you can see here again that fine-tuning on our subset of CCNet increases perplexity a bit. But this is just because CCNet is not as close to Wikipedia as the original subset of the pre-training corpus. The interesting bit is that as we move from GPTJ plus CC to Toolformer, we do not see any change in perplexity. So including API calls in our pre-training data does not hurt perplexity. The reason why we're only seeing Toolformer disabled here is that as soon as we enable API calls, computing perplexity becomes intractable, because at each possible position to get the distribution over next tokens, we would have to look at all possible API calls that the model could do. And we see a very similar trend for the other data set, a subset of CCNet that we did not use for training. So here you can see that as we move from GPTJ to GPTJ plus CC, perplexity actually goes down, because now we're looking at the exact same distribution that the model is also fine-tuned on. And again, we see no difference between the regular model and the one trained with API calls. All right, so far we have looked at only a single size, at only a single model, which is our 6.7 billion parameter GPTJ. And so, of course, we were interested in seeing how model size actually affects the ability to use tools, because there were 2 things that we were speculating about, or 2 things that we could imagine. One of them was, as the model gets bigger in size, it might need those APIs, it might need those tools less and less, because it becomes better at doing stuff itself. So we might expect that as the model size increases, the advantage we get from using tools becomes less and less. On the other hand, you might also think that as the model gets bigger, it becomes better at learning how to use those APIs. So it will make better API calls, and accordingly, the gap might also grow bigger. And because obviously we did not know which one of those it would be, or whether there are any other factors, we just tried different model sizes. And basically, we used all the GPT-2 model sizes from 100 million to 1.3 billion parameters plus GPTJ, and used both the Toolformer variant that uses API calls and the one where they are disabled. And so what we can see here is average performance on the Llama benchmark. In purple, again, we see GPT-3, and then there's different Toolformer sizes. The interesting bit is the 2 smallest models that we tried can't use APIs at all. So we see no difference between Toolformer with API calls and Toolformer without API calls. But as we move to around 1 billion parameters, we can see that suddenly there's this difference in performance. Suddenly using APIs helps. And then as we move to 6.7 billion parameters, the gap remains kind of constant. So it doesn't get less useful, but also not really more useful. We see a very similar trend for our math benchmarks, where again, the 2 smallest model sizes don't make use of tools at all. But then as we get to 1 billion parameters, things start to work and our gap remains constant. Things look a bit different for the question answering benchmark, where the tool being used is the Wikipedia search. First of all, we can see that it's already useful for the 2 smallest models. That might be because this tool is much easier to use. For the question answering tool that is used during Llama, you need to formulate an actual question. For the calculator tool, you need to put in some meaningful numbers. But for a Wikipedia search, you just need to put in 1 or 2 words that are roughly relevant to the topic, and you might already get something useful. So in a way, that is the easiest tool to use. We can also see that as we move to the biggest model size, the gap gets a bit smaller. We are currently investigating what happens as you move to 30 or 70 billion parameters. But I don't have any slides for that yet. All right, I'm almost at the end of this talk. I do have one final slide containing a few things that I personally think would be interesting for future work. In general, I think tool use is kind of a hot topic right now. There's basically 1 or 2 new papers around this every day. It's kind of hard to keep track. And I do think there's a lot of super interesting ideas to explore far beyond the few things that I've listed here. Still, those are the things that I'm personally most excited about in the moment. The first one here is what I call interactive, chained, and hierarchical tool use. All of those are 3 slightly different things, the way I think about them, but still very closely related. What I mean with interactive tool use is that if you have a tool like a search engine, where you can get multiple results, you maybe want to have a more interactive experience, where first you do your query, you get a result, and then you say, this doesn't quite look like what I was hoping to get. Can you maybe show me the next result? Or maybe you reformulate the query a bit to get something better. Chain tool use would mean using multiple tools in a row. First, you take the calendar to get the current date. Then you use that to ask a question, something along those lines. And hierarchical tool use, something that we tried for this paper but didn't quite get to work, is to have the language model be its own tool. So in addition to being able to call other tools, the model would also be able to call itself with a certain prompt that would, for example, encourage it to reason about something or to think step by step, have some kind of scratch pad to take some notes. Obviously, if a model can call itself, it can also do so recursively, and that will give you some kind of hierarchical structure where a model could call itself, then call itself again, etc., which I think is a fascinating idea, but something that we haven't tried yet. Another more obvious thing is to combine tool use with instruction tuning and more powerful models, because this is where a lot of the field is going right now. And obviously, it's much more interesting to have a model that actually is aligned with your intents and to play around with that rather than a vanilla language model. There are some interesting research challenges along the way when you try to combine this idea with instruction tuning. So I do think there's quite a bit of interesting research to do to get that to work well. Then another obvious thing is to integrate more advanced tools. Let's say a Python interpreter, database access, user data to get a more personalized experience, some reasoning. All of this has already been tried in some ways. It's easy to get that to work somehow, but I think it's really hard to get it to work really well. So even though all of those things have already been tried, I still think there's a lot of work to do. In general, more advanced algorithms to improve tool usage would also be interesting. We're exploring some reinforcement learning ideas here, which seems like a very natural fit. One thing that I'm a bit more careful about is what I call moving from passive to active tool use. So all the tools that I've shown you and all the tools that we've worked with here are kind of passive, that they just provide some additional information, but don't actually change the world state in any way. You might think of tools that are a bit different, that are more active, and that they could, for example, send an email, post something on some website, turn on the lights, these kinds of things, which are very interesting and potentially very powerful. So there's a lot of great things you could do with that, but also there's a lot of risk attached to that, especially given how little we understand about large language models these days and how uncontrollable they are in some cases. So I'm personally very, very careful about this. I think it's an interesting research direction, but I think it should be approached with great care. One should definitely think about safety implications first and how to make sure that things do not go wrong. And I do think that this is a major challenge. And then the final thing on the list here, which is in no particular order, is we were also thinking about ways to improve self-training, for example, by leveraging negative examples or using iterative training, just to make things more efficient so that we don't have to annotate millions of examples with API calls and then throw away 99% of it. All right, that is it basically from my side. So thank you very much for listening.
Thanks, great. Questions from the audience? Have any questions?
I have a question.
Sorry, proceed.
Yes.
From your experience, how reliable and accurate are likelihood estimates that LLMs provide. And did you consider eliciting a likelihood estimate from a model that is different from the one that produced the answer?
So I'll start with the second question because that's the easier one to answer. We did not try that. We always really kept the same model throughout the entire pipeline. As I've said, I do think it's important that the model that actually is used to filter the API calls is the one that we actually train in the end. But of course, you could think about using a different model to generate them in the first place. But this is something that we haven't tried. In terms of how reliable those likelihood estimates are, there are certainly many cases where you can see, for example, that an API call is considered helpful simply because it contains some words that we also find in the continuation, but there's actually no real correspondence between them, or it's just like a random match. So we certainly have some of those cases. My experience is that those become less as we move to more powerful models. So more powerful models seem to be less kind of prone to rely on simple heuristics like does the word occur somewhere in the previous context for getting the probability distribution. So to some extent, the problem gets better with that. The other thing I have to say is it's actually not that bad to have a few examples in our training corpus that are not good, like a few examples when API call is considered helpful based on our likelihood estimate, but actually it isn't. Because having a few examples where the model does API calls and then they're not helpful, they can't be used in any way, makes it a bit more robust to them. And so that means if you have an API call, it doesn't give you any useful information. The model doesn't just start copying something from it, but it actually just ignores it, which is a nice ability to have. Still, I do think, like, obviously there are flaws with likelihood estimates. If you look at the examples of API calls that we keep, there's still a lot of noise sometimes. And so trying different stuff, like trying RLHF kind of things to see which API calls give you a better response or similar ideas, certainly something worth exploring, but not something that we've done yet.
More questions? Let's see, I mean, it seems like
just a quick question. Have you tried playing around with integrating this with like Wolfram Alpha or something?
We have not tried that. Like we've had that idea a while ago. It's we did not do that in the end because obviously we need to use an API quite excessively to get all those sampled API calls executed and everything, which is a bit tricky to do if it's not an API that you have like full control over and can just easily run for millions of times. I do think that would be a super interesting addition. I would love to try that, but it's not something we've done yet.
Got you. And just quick other future possible direction. I was thinking about like, if you could use this large language model to call on a more specialized, smaller large language model. For example, if you have to do some sort of legal reasoning task, you might have like a LLM trained on law data, and this could call towards that.
I think that's a super cool idea. We actually tried that with a model that was specifically trained on scientific text to see whether our model would learn to use that specialized model then. We didn't really get that to work reliably. It would kind of like, it was a very noisy thing that we got. So in many cases, it would use that other large language model despite the text not being about scientific stuff. I do think we just haven't tried hard enough here yet. I do certainly think that's a great idea. It's kind of like similar to mixture of experts, but in a more like explicit way. I do like that a lot, but yeah, so I think that's really something that deserves further attention.
Matt?
Yeah, just do you know the Bing search engine, which seems to actually interface very well with external software and does searches? Do you know what algorithm it's using to do that?
I think as with most things from OpenAI, it's or like Microsoft in that case, but still it's very hard to get any information about what is going on under the hood. So based on, I can just speculate about that. But I would assume that it's probably similar to, let's say, for example, what OpenAI did with WebGPT, which would be this approach where you just annotate a lot of examples with humans. So that would be my best guess, that they would just collect a lot of different inputs, let humans write search queries and then train on that, which I think for this tool is a perfectly reasonable approach. But again, like I don't know anything about that. That would just be my theory if I had to guess.
Okay.
More questions? If not, well, let's thank Timo for very interesting talk. Excellent. Very
Yeah, thank
nice.
you for having me.
Sure, happy to.